Hello students, welcome back to my YouTube channel. Today I will explain one of the important problem related to CSIR net. Question number 28, part C, CSIR net mathematics. First understand the problem. It has been asked in February 2025, part C, question number 64. For each positive integer n, define fn is a function from the closed interval 0, 1 to r by fn of x equals to n into x into 1 minus x to the power of n. Which of the following statements are true? Which of the following statements are true? Option A, fn n greater than or equal to 1 does not converge pointwise in the closed interval 0, 1. Option B, fn n greater than or equal to 1 converges pointwise to a continuous function on the closed interval 0, 1. Option C, fn n greater than or equal to 1, that is converges pointwise to a discontinuous function in the closed interval 0, 1. Option D, fn n greater than or equal to 1 does not converge uniformly on the closed interval 0, 1. First write down whatever the given fn of x equals to nx into 1 minus x to the power of n in the closed interval 0, 1, where n equals to 1, 2, 3. Now I will consider, let gn of x equals to nx and hn of x equals to 1 minus x to the power of n. We know that because it is given in the closed interval 0, 1. This is 0, this is 1, x is any arbitrary. Now what we will do, we will check the behavior of 1 minus x to the power of n and the behavior of n into x. So for all, it is in the closed interval 0, 1. The domain has given this is 0, this is 1, this is any x arbitrary. This is 1 minus x. If x equal to 0 0.5, x equal to 0 0.5, you take, then 1 minus x equals to also 0 0.5. If x equal to 0 0.1, 1 minus x equals to 0.9. If x equals to 0, then its value is 1. If x equals to 1, its value is 0. Means whatever the value take x in the closed interval 0, 1, 1 minus x values also lie in the closed interval 0 comma 1. This I want to say, because you can take any arbitrary value x, 0.5, x equal to 0.5, substitute this x equals to 0.5 in this one, 1 minus 0.5 equal to 0.5. Again this value lies in between the closed interval 0 comma 1. Again, whatever the value you take in the closed interval 0 comma 1, 1 minus x value also will be in the closed interval 0 comma 1. I want to say this one. Now I will raise the power, because as we know that 0, this is 0, this is 1, and 1 minus x values also will lie in between 0 and 1. I will take in between 0 and 1. In the closed interval 0 comma 1, I will take 0.3 or 0.4 or 0.5, whatever the value you will take. But for some example I am taking now 1 minus x equals to 0.3. You can take 0.4 also, you can take 0.5 also, but it should be in the closed interval 0 comma 1, because we know the value of 1 minus x will lies in the closed interval 0 comma 1. Now 0.3 to the power of n tends to 0, that is 0.3 into 0.3 into 0.3. As n tends to infinity, it approaches to 0. As n tends to infinity, it approaches to 0. It shows that as we increase n tends to infinity, it is approaching almost equal to 0. Therefore 1 minus x to the power of n tends to 0 as n tends to infinity. I think this step is clear for you. Now separately we will calculate gn of x. Gn of x equal to n into x in the closed interval 0 comma 1. As n tends to infinity, what happens to nx? Again I will take x equal to 0.3, that is nx is equals to n into 0.3. As n tends to infinity, the value is also reaching to infinity. In this case, as n tends to infinity, the value is also approaching to infinity. Now you will substitute here, because fn of x equals to gn of x into hn of x. We have taken this gn of x is equal to n into x. This is 1 minus x to the power n. So this approaches to 0 as n tends to infinity, and this approaches to infinity as n tends to infinity. If we multiply this two, limit n tends to fn of x equals to 0, means it is a pointwise convergence. It is a pointwise convergence, because we have evaluated at each x. For example, we take some number gn of x 2, hn of x 3, because gn of x is tending to infinity as n tends to infinity, and hn of x tending to 0 as n tends to infinity. So this is gn of x increasing because it is increasing to infinity, 2, 2.5, 3 up to infinity, and this is reducing because as n tends to infinity, its value approaching to 0 means it is reducing to 0, 3, 2.5, 2, and so on. So here we can say that it is nearly approaching to 0. Now we conclude with some examples that we have now concluded with some example that gn of x into hn of x equals to 0. You can see the graph, this one, and you can see the graph, this one. Therefore, fn of x tends to 0 as n tends to infinity for all x belongs to the closed interval 0, 1. Now, 0 is a constant function and constant function is a continuous function. That is, fn of x is a continuous function. Now, you can check the option. What is the option? Option A, fn does not converges pointwise. This is wrong because it is converging pointwise. Fn n greater than or equal to 1 converges pointwise to a continuous function. B is the right answer. Now we check these two. Converges pointwise to a discontinuous function. No, this is also wrong. Now we have to check option D, whether it is uniformly converges or it does not uniformly converges. To check the option D, what to do? Now, fn of x equals to n into x, 1 minus x to the power of n. This is given. I will take f dash of n of x. I will differentiate it, and this will be the final step. Now we find the stationary point, that is fn of x, f dash n of x equal to 0. N is a positive integer. Therefore, 1 minus x to the power of n minus 1, either this should be 0 or this term should be 0. Now we check 1 minus x to the power of n minus 1 equal to 0, but 1 minus x to the power of n minus 1 tends to 0 as n tends to infinity, but for a finite n, it is cannot be 0. It is cannot be 0. For finite n, it cannot be 0. Therefore, 1 minus x to the power of n minus 1 is not equal to 0. If this is not equal to 0, then this step should be 0. Then finally we got x equals to 1 divided by n plus 1. That is, at x equals to 1 divided by n plus 1, for f1 it is a stationary point at 1. Now we got the general term, that is, now I will find for f1 of x equals to 1 divided by 1 plus 1 equal to 0.5. f2 for f2 of x I will find 1 divided by 2 plus 1 equal to 1 by 3. That is this is 0, this is 1, this is 0.5, this is the stationary point, this is for f1, this is the stationary point for 1 by 3. Now general, that is 1 divided by n plus 1. Consider this point as a 1 divided by n plus 1. At this is the stationary point. This we have got general as 1 divided by n plus 1. At the stationary point, what is the value of the function? So at f1, f2 we can find it. See, what is the supremum? Supremum x belongs to the closed interval 0, 1. Fn of x equals to limit n tends to infinity. The answer will be nearly 0.36. This is 0, this is 1, this is 0.5, this is the first stationary point. Call this as f1, this is 1 by 3, this is the f2 stationary point, and this is 1 divided by n plus 1, that is equals to 0.33. Just I am roughly taking the graph. This is the stationary point. If we know the stationary point, we can calculate its functional value. Example, now we got 1 divided by n plus 1, its value is 0.33. Or you can check here is also for f1 of 0.5 equal to 0.5 into 1 minus x. You will get the function value. At this stationary point, this is the functional value. At this stationary point, this is the functional value. That is f2 of 1 by 3 is equal to, you will get this function value. So what is the conclusion? At each value of x, we evaluated fn of x tends to 0 as n tends to infinity. Fn of x on 0, 1, it is not approaching to 0. For uniform convergence, it is not approaching to 0 because it is approaching to 0.33 nearly. This is f1, this is f2, this is 1 divided by n plus 1, this is nearly equal to 0.33, and this value is 0.5, and this is stationary point is 1 by 3. So what we conclude that for uniform convergence, for pointwise convergence, it is a pointwise convergence. We have proved already it is a pointwise convergence, but it is not uniform convergence because it is not approaching to 0. It is not a uniform convergence. So the option D option, we will check now. Fn does not converges uniformly. Yes, it is correct. And this one wrong. And this one correct. And this one wrong. Students, I hope you have understood this question. Next time, again, some interesting question I will solve. Thank you so much.